So far, we've been talking about gases, right? And we've learned two laws so far. First one, Boyle's law. Somebody tell me what Boyle's law is? It is. There is an inverse relationship between pressure and volume. So what does that mean if I were to write that as an equation? P1, V1 equals P2, V2. Okay? Second law we learned the other day. Charles' law. Anybody? So how do we write that as an equation?
V1 over T1 equals V2 over T2.
Exactly. So, you know, when two things are multiplied together, they're inversely related. This should remind you of when we did pH, right? Hydronium times hydroxide. The two are multiplied together are constant. So when one goes up, the other one has to go down, doesn't it? Just like Boyle's law. When things are multiplied together, they are inversely related like this. Now, look at Charles's law. They're not multiplied, they're divided, right? So because it's a ratio, volume divided by temperature means that they're directly related. As volume goes up, temperature must go up. Now, we didn't do this outside because it was hard. It's harder to do this one. This tells us that the pressure must remain constant. So we have to change the volume as the temperature increases to make the pressure constant. It's a little bit hard to understand conceptually. So, we have a new law. This is a French guy, so this is not gay anything. This is Guy. Okay? This is Guy Lussac. And his law relates pressure and temperature. And they are directly related. So if we look back, and here's Charles's law, they're directly related. As one goes up, the other one goes up. What would you think that the equation for pressure and temperature should be? Without looking at the book. Think about it. If Charles's law was a ratio, what do you think Gay-Lussac's law should be? Should it be like Boyle's law and the two multiply together, or should it be a ratio? Should be a ratio, right? Because they're directly related. As I heat something up, as I heat the gas up, the pressure goes up, right? Remember we did that the other day? We heated you up, we made you move faster, and the pressure went up. Okay? So we're going to have P1 over T1 equals P2 over T2. Okay? Fair enough? As I heat you up, you move faster, and the pressure goes up. You can do this at home. Actually, this one is, Charles's law is the one you can do at home with the balloon in the freezer. It's real easy to do. How can you do pressure and temperature at home? Anybody here ever done pressure and temperature at home? Sort of if you have a pressure cooker, right? As the temperature goes up, the pressure goes up in it. Here's a really bad way to do it. Take a sealed can and sit it on the stove. What do you think would happen?
It's going to explode.
Why?
Because the pressure builds up in it.
The pressure builds up inside of it because you convert a lot of atoms or a lot of molecules into gas, right? So the N actually goes up. But the temperature goes up, so those molecules are moving faster and faster. The pressure goes up, and then until eventually what happens? Something's got to give somewhere. And you got beans all over the house. Try it at home. Not at my home. You still live at home? don't know what to do with it. You might get it. But I would work with it. It'd be a good demonstration, and you could just tell. You could, yeah, you could do it outside on your like camp stove, or you could just tell your mom, "Look, Mom, it was a chemistry experiment. My instructor told me to do it." What do you think?
Yeah, she'd be like, would you jump off a roof if you told me to?
Yeah, that's what moms say. Moms take the fun out of it, don't they? So, okay, so here's Gay-Lussac's law, pressure and temperature. So, they're directly related. We're not going to worry about solving it for one. Can you guys do this problem? Remember, what's one of the keys for temperature? What do we know about temperature? Must be in Kelvin. Very good. Angers me. Think about the problem before you start punching the numbers. Why should you think about the problem before you start entering numbers? Because if you don't, you have no idea if the answer you're going to get makes sense or not. So what do we have? T1 is 2.0 atmospheres. What's T1? 291? Is that right? Equals P2 over 335 Kelvin. So before I enter any numbers, I'm going to think, hey, the temperature went up some. Did it go up a whole lot?
No.
It went up a little bit. So if I get an answer that's like 20 atmospheres, is that a right answer?
No.
If I get an answer that's 0.2 atmospheres, is that right?
No.
No, because pressure's going to go up. And it better go up just a little bit, right? This goes up. When I look at this, I kind of see this going up about 10%. Because I think, that's how I think like that. Because it goes up about 40 out of 300, that's roughly 10%. So I better get an answer somewhere around 2.2, 2.3. What'd you get?
2.3.
2.3 atmospheres?
Yeah.
All right, if you don't know, how did we solve this? You guys, a bunch of cross multipliers? Multiply these two together, then divide by that one. What if I want to divide these two and then multiply by that one? Is that okay? That's okay too. More than one way to solve an equation, right? Most of you will multiply these two and then divide by the one that's left over. That's a good way to remember it, right? Multiply your two numbers and divide by the other one. Everybody get 2.3. We're all good? Okay. What about this one? Does pressure have to be in atmospheres?
No.
No. You can do it in Thor or millimeters of mercury, it doesn't matter. So you got to start punching numbers, you don't even think. This problem has a joke in it. See, if you don't write things down, you don't see this. Pressure 1 is what? 645 torr. 120 degrees C is what? 401. People write these questions have a sense of humor, right? And what happens? The pressure goes up. How much does the pressure go up? Quite a bit, right? It goes up like almost 200 out of 600. So it's like a third. So the temperature better go up quite a bit too, right? So what's my final temperature in in Kelvin, sorry. My final temperature in Kelvin, it better go up like 100 degrees at least, or 100 Kelvin. Huh? 512 Kelvin. Did it go up a reasonable amount? Well, look at how much the pressure went up. It went up pretty good. The temperature went up by 100 Kelvin. That makes sense, right? And the question says Celsius, and we're not done, are we? So T2 in Celsius is 512 minus 273, so it is 239 degrees C. See why you should think about the problem first? Is there anybody here can answer this question? Below the sea? What does boiling mean? What happens at boiling? Do it. And what does it mean that it's boiling? What does it mean? What's it doing? It's doing what? Temperature is staying constant, right? What's happening? Change of state. Going from what? Liquid to a gas. What does that mean? It means little water molecules are shooting off, right? Turning into a gas. All right. Well, at sea level, I have 1 atmosphere pressure on here, right? What about that's preventing these molecules from jumping off? Well, what about when you go to Denver? If this is how much pressure when I go to Denver, my arrow might only look like that. It's not as big as that one is it? So it's not keeping them on there as much, is it? So water boils at a lower temperature when you go up in the mountains. Does that mean anything to you? No. You do any cooking? You ever boil an egg? If the water's not as hot, because it boils at a lower temperature, you think it'll impact how long you gotta boil your egg? Yeah. Okay. So it does mean something, right? So when you travel, or if you ever move to the mountains, know that your water will boil at a slightly lower temperature. That's why that's why cooking times change when you go up in elevation. You move to Denver, you have to boil your eggs longer because the water's not as hot when it boils because there's not as much pressure holding the water molecules on there. You think anybody cooking dinner at home really thinks about that when they're cooking? That's too much thinking when you're cooking, isn't it? But that's what's really happening. Now, if you guys ever go to Denver and cook, then you'll know. What? What you need? What'd you leave?
All my stuff.
Oh.
All my important stuff. Sorry.
That's okay. We're talking about cooking in Denver. Boiling eggs.
Nice. I like it.
You like my graphic?
It is. It's beautiful.
Thank you.